Hello together. Today I want to go on with our exercise. We have here the exercise 1, problem 5. And today we want to discuss the quarter wave transformer. It's written that an antenna with an input impedance of 10 ohm is to be connected to a coaxial cable with a characteristic impedance of 50 ohm. Design an air-filled quarter wave transformer to match the antenna to the cable at 900 MHz. So from the lecture notes we know if I have a quarter wave transformer, this is just a transmission line with a certain characteristic impedance, and it must have the length of a quarter wave at a certain frequency. And in this case we know that the load resistance will be transformed into an input resistance according to this equation here. And with the help of this equation we can now calculate the characteristic impedance of the transmission line. And in the next step we will do this. With our values here we will get a characteristic impedance of 22.4 ohm. So we must use a transmission line with this characteristic impedance. And if I want to have that the quarter wave transformer works at 900 MHz, we can calculate the wavelength. So at the moment we assume here a air-filled transmission line, though the wavelengths will be equal to C naught over F naught. And if I take the value, a fourth of this value, then we end up in a value of 0.0833 meter. So to get an idea of the frequency behavior of a quarter wave transformer, I will now switch to our simulation. In our simulation, here we have our simulation tool, and I already included the elements. We have here the load resistance of 10 ohm, and then I have a transmission line here with a characteristic impedance of 22.4 ohm, and it shows a length of 83.33 millimeter. And now we can analyze, for example, the parameter S11. Sorry, it's already fixed, so we can analyze now. And here we see the frequency characteristic. So we designed this quarter wave transformer for a frequency of 900 MHz, and you see here at 900 MHz we will have a nice matching of to the 50 ohm transmission line. But you see, of course, it's not very broadband. If you want to have a broader bandwidth in this region, you must use more quarter wave transformers. So this will be discussed in a later exercise. So now we can go on with our next problem. In our next problem we will discuss the following problem. We have here, I assume, to have a transmission line, a coaxial transmission line, and to center the inner conductor of the coaxial transmission line we need a dielectric support. Its electrical influence may be modeled by a parallel capacitor of 0.1 picofarad. So the equivalent circuit of this situation is this. We have here a 50 ohm transmission line, here a 50 ohm transmission line, and in between we have this capacitor, and also the transmission line is terminated in its characteristic impedance. And now the question, up to which frequency the coaxial transmission line may be used if the reflection coefficient of the support must be lower than -20 dB. Of course the support is now represented by this characteristic impedance, by this capacitor. And of course, since we have here, perhaps I switch back again, since we have a parallel connection between the capacitor and the terminating resistor, we should switch to admittances. So if I want to calculate the reflection coefficient of our support, I will use this equation to calculate the reflection coefficient, and this equation is valid for the admittance. We have the characteristic admittance of the transmission line minus YL divided by the characteristic admittance plus YL, and the load admittance is now given as the parallel connection of the characteristic admittance of the transmission line plus J omega C. And if you insert this equation here, then you end up in a RS. According to this, we have minus J omega C divided by 2 YC plus J omega C. So since the susceptance of the capacitor is quite small, we can now use the following equation. So compared to the conductance here, this value is very small, and so we can neglect this value, and we end up in this expression for the reflection coefficient. And if I insert instead of YC ZC, then we end up here in this equation for RS. And the problem is now that the RS is given in dB. So if I have a reflection coefficient which is given in dB, then we must know how the dB value is defined. And there exists a different notation in the literature, and I use in principle this notation, which says the absolute value of RS in dB is equal to 20 times log the absolute value of RS. So from a strict mathematical viewpoint, this equation is wrong. So normally you should insert here another or use another value here, but from a physical point, I can argue I can give RS in dB, or I can give RS in a linear scale. So if I want to transform this from the dB scale into the linear scale, I must use in principle this equation. RS is equal to 10 to the power of RS divided by dB divided by 20. So as soon as RS is given in dB, like here, you see first the dB will cancel, and we will have the absolute value of RS is equal to 10 to the power of minus 20 divided by 20. It's 10 to the power of minus 1. It's just 0.1. So we see now, as soon as I have a reflection coefficient of minus 20 dB, then this corresponds to an RS value in the linear scale of 0.1. So now we can go back to our equation. If I just calculate the absolute value, then you see that J will disappear, and I can form an equation for the frequency. Only below this value of the frequency, the reflection coefficient will be lower than minus 20 dB. And if you calculate the value, then you end up in a value of 6.37 gigahertz, which corresponds to round about 6.4 gigahertz. And also this, I want to have a look now to this task with the help of the simulation tool. So again, in the simulation tool, I prepared now our setup. We have here the 50 ohm load impedance, which the 50 ohm transmission line is ends up in this load impedance. And here I have the 0.1 picofarad capacitor, which represents our dielectric support. And here we have again the 50 ohm transmission line. So the length of this transmission line, they don't play any role, since we are only interested in the absolute value. And now we can analyze this situation. And here you see now the reflection coefficient. And if I now switch on the marker, then you will see that as long as the frequency is below 6.4 gigahertz, we are lower than 20 dB, which also shows that our approximation is quite reasonably. So this finished the exercise again, and thank you for watching the video. As always, your comments are welcome, and I hope to see you again.